This is my Oscillations Lab for PHYS 2211. To begin, our mission here is to investigate the oscillatory motion of a hanging mass attached to a spring that swings in an arc-like motion. And what models and principles we use here? They include the tracker app, which I use to track motion in a video, GlowScript model, which I coded to predict oscillatory motion with a computational model, and lastly, the energy principle, which dictates what we're actually investigating with this lab here. And what will happen? We will see that our model will closely resemble the motion seen in the video, and the total sum of the changes in energy will also equal zero as stated by the energy principle from prior, and it will be very accurate in our findings. What are our physics ideas? They include the energy principle, which says that the change in energy of a system equals total work done by the surroundings plus thermal energy exchanged with surroundings. And since there is no thermal energy change here at all, really, Q is just negligible, and W can be found as the change in energy from the outside forces, which is also going to be zero because there's no change in energy, as shown by our graphs later on in the slideshow. Following Newton's second law, we can derive some formulas as well from that, which include the velocity update formula and also the position update formula, which are given as Vf equals Vi plus F over m times delta t, and Rf equals Ri plus V delta t. And our energy formulas are derived from integrating the force with respect to the displacement, and K is 1/2 mv squared for kinetic energy, Ug is mgh for GPE, and Us equals 1/2 ks squared for spring potential energy, and those are our big three for this experiment. Here's a tracker data that I use to analyze the sample video and extract every position data at every point in the video in order to predict the motion or find the motion data in table and graph-like form. So here's the video that I used to extract from, 10 seconds long. It's swinging in like this parabolic sort of arc motion, and it's going back and forth, back and forth, back and forth. So pretty neat. And the next slide. Coding implementation part 1. To predict the motion of the swinging mass, I use GlowScript to create graphs of predicted motion versus observed motion, as well as changes in energy. So I use the provided constants in the pre-lecture videos to set up my code, which includes constants like spring stiffness, or K spring, the relaxed length of the spring, or L naught, and also the mass of the system, etc. Here's a link, and here's also the code that I use, which includes the setting up the initial conditions, like position, velocity, given in the actual table data, and the mass, etc., the time, delta t, as well as, gravity constant, K, L naught, and formulas for L hat, and S for spring length change, as well as energy formulas too. So here are the graphs that I got from my code from before and from this code too, which includes the loop for changing the energy and force at each iteration and making sure that the non-constant forces like the spring force and gravitational force are accounted for and properly changed at each time interval. And we found that in the total change in energy versus time graph, the change in energy is going to be zero because there's no net force acting upon the system that causes work. So energy in total is constant, although the individual energy components are changing in this oscillatory wave-like motion. So it's pretty cool to see all these different colors and what they correspond to energy-wise, like delta K, delta U grav, etc. And here is the red versus blue. The red is the experimental data from tracker, and the blue is what I predicted, and they're very similar in actuality. So in both the X and Y directions, it was accurate and deviated only a little bit from the actual data. Now, what are the differences? As I said just now, they're very similar in either dimension, and the deviation might be due to either clumsy calibration of tracker with human error and or forces that aren't accounted for, like drag in the real world, that might have caused some work to be done. What are some possible errors? Although we assume that the system is closed, in other words, there's no work by the surroundings, there are most definitely external forces acting on it that produce a non-zero amount of work, like drag. I might have misaligned the center of mass and tracker while I was rushing through the frame, so the observed graph appears to be jagged at certain points that could have been more smooth. And is the energy principle satisfied? Yes, because there are no external forces acting on the system, and therefore the change in energy, or the yellow horizontal line here, is just zero throughout and throughout. And although the different types of energy are changing throughout the experiment, their sum, or the total line, is just a horizontal line that's zero. So they vary throughout the entire experiment, throughout the change in time, but the total energy is always going to be zero, no matter what, because of the energy principle. And the oscillatory periods, I found those by basically looking at the distance between the two between three peaks and looking at their average distance. And as you can see here, the x position graph at the period that is 1.667 and y is 1.540. So as you can see, choosing two different dimensions will result in oscillation periods that deviate from each other a little bit, and thus affects the spring constant k and the appearance of the graphs. And therefore, if you look at the graph here, the x position graph looks a little bit wider physically than the y position graph because it is a larger period. And a period can be found by using, for example, peak to peak and the distance in between them for time. All right, thank you. That is all.